Great. So thank you very much, Philippe. I will try to stick to my time slot. So I'm going to talk about status and challenges for forest biomass change monitoring from Earth observation. I work at the University of Leicester and the National Centre for Earth Observation in the UK, and I am leading the work package 3000 in the ESA Biomass CCI Plus project on biomass change. The partners of this work package are shown on this slide, and we aim to map the magnitude and direction of change at a global level, but also quantify the uncertainties of the estimates. And there are a number of challenges in doing this. One is the different input data that have been used for different epochs for generating global data sets, different sensitivities of sensors to biomass, for example, and how the biomass retrieval algorithm responds to them in the phase 1 CCI project and in GloBiomass, and also the variable availability of reference data for the different time periods or epochs to validate the change. The work package has 3 main tasks on the community engagement, of which this event is part, the assessment of different methodologies for biomass change, and the uncertainty characterization. Where we are after the end of phase 1 of the Biomass CCI Plus project is that we are basically having these above ground biomass difference maps. Here is one from 2018 to 2010. So the growth or loss of biomass over these 8 years in tons per hectare. And that is accompanied by a product on the quality of the estimates, which is on the right-hand side here. That means actually here, most of the changes are labeled as improbable according to this. The only areas, or predominantly the areas with confidence that we can detect, are areas of clear cut, where we have a very clear loss of a large amount of biomass. The more subtle increases of biomass are harder to detect with confidence. Now, as we're moving into a scenario for biomass change production in the current phase of the CCI Plus project, more and more biomass stock maps will become available as the CCI Plus matures and the project progresses. How do we best estimate biomass change between 2 time points out of this? On this slide, you see different annual maps of a small part of the Congo Basin for different years. We have produced this by Pedro Rodriguez Vega et al. Have produced this in the National Center for Earth Observation. And as we build up the time series of different biomass stock maps, some of the information content on biomass change is going to be in the stock values at times 1 and 2, let's say 2008, 2010, or 2020. We can estimate biomass change as the difference between 2 different stock maps. That's one approach. But there is some additional information contained in the biomass time series of each pixel. So especially the more time periods we build up and we stack those on top of each other, we can estimate biomass change as the trend over time or as a possible sudden disruption of the value if it drops all of a sudden due to logging. Inherent in all of this is the biomass change uncertainty characterization, where we have to actually estimate what the precision of the estimates is and what the bias is. Precision and bias are the terms we prefer to use because uncertainty encapsulates all and means different things to different people, whereas precision and bias have clearer statistical definitions. What we need to do in this task is basically to review and assess candidate change algorithms and their applicability to the current production scenario in the CCI. Now I'm going to show you an animation here of the maps that I've just shown for the Congo Basin for a different area, where you can see a time series of the maps from 2007 to 2017. And you can see here the deforestation and biomass loss in tons of carbon per hectare happening over this area. And there is very clearly some information in the temporal trajectory of the different pixels. It is not just the change we estimate between time 1 and time 2 that matters. There are different candidate algorithms for biomass change. These can be described in broadly 2 different types of methods. One is indirect estimation, where we can model the relationship between the response variable or biomass change in this case and the Earth observation variables at 2 times, and then estimate the changes as the differences between the model predictions. So this is the stock differencing. And then we have the direct estimation, which models the change directly using observations of the biomass change in response to the different Earth observation variables for 2 different dates. The direct method is generally preferred by people who have published on this, although a few statistically rigorous comparisons have been reported. There are not many studies that compare these different methods. Ron McRoberts et al. 2015 found actually that the indirect method gave a more accurate result of biomass change. So it's not always the direct methods that are giving better results. An example of a method for looking at the temporal trajectory is the land trender algorithm that is available on Google Earth Engine. The link is on the slide here, on this web link at the bottom. And that basically looks at spectral indices, in this case, over time. And it segments the time series into periods of time where there is no change, where there's a sudden drop, or where there is a steady increase. And it fits different lines or line segments to those different parts of the time series. So it is a possibility to think about that as a long-term ambition for biomass change production, that we can think about the temporal content of information in the data. Canopy structure can be an important auxiliary variable in estimating biomass change. Indirect above-ground biomass change estimation from canopy height performed better than the direct estimation if it was helped by TandemX digital surface model texture. In this case, this was the paper by Knapp et al. In 2018 in remote sensing. They basically look at the texture in surface height. And what they found basically is that you can improve the estimate of biomass change by looking at the variability of very high resolution surface models of the canopy. So it's also possible to think about biomass change as a multi-parameter problem. And I want to talk about precision and bias a little bit more. Precision is characterized by random errors in the biomass change estimates. So the precision you can think of as the scatter around the value that we estimate. The precision is scale dependent. We know this from past work that basically a coarser aggregation of biomass change data through pixel averaging can increase the precision or reduce the random error at the coarser spatial scale. Bias, on the other hand, is the systematic error of the biomass change estimates when compared to a true value or theoretical value, which could come from forest inventory plots. So you can imagine if you have a dartboard and you throw a dart, the bias would be if your dart always hits the bottom right corner of the dartboard. So the bias can also be scale dependent on the spatial scale. And the biomass stock estimates actually have shown in phase 1 that the bias is also dependent on the magnitude of the biomass stock itself. So when you look at low biomass pixels and high biomass pixels, they can have different amounts of bias in the estimation. What does all that mean for the biomass change production? For biomass change, we need to devise methods for reducing the bias and for increasing the precision, clearly, the same as we do for the stock production, the biomass stock map production. And in our considerations, trade-offs are likely between the spatial scale or resolution of the biomass change product and precision and bias. And to summarize, the challenge is in the production of consistent biomass stock and change maps. So that means the change is consistent with the stock 2 minus stock 1 values while reducing the bias and increasing the precision. We need to decide how we use the temporal information content in the biomass stock data in the temporal stack, and we will compare and evaluate algorithms to decide how we progress. Thank you very much.
Thank you very